Hello everyone, let's talk about our 4.03 heat transfer lab. So what I have is I have your lab here. I'm just going to walk through it, kind of tell you what, I put, check your answers. If you have questions, let me know. So you had a lot to do actually in this lab. There was videos, there was extra, links to go in and look. So hopefully with all that, you got a pretty good understanding of a calorimeter and how to do these calculations and stuff. So go ahead and notice here the word great. You'll want to write that down. Okay, so let's go ahead and start here. So you can see, right here at the top, you got what calorimeters you use. So we measure that enthalpy of fusion for water, right? So that was ultimately what we did at the end. So we're studying that heat transfer, right? How much energy is getting transferred from one thing to the other without getting lost in the surroundings. That's the goal. So hopefully you got to observe and use that closed system with your virtual lab. Yeah, the limitations of a simple calorimeter, we can't do too much with it. If you did any research, you'd see things about bomb calorimeters too that they use when you're doing, what's it called? I'm having a brain freeze. Exothermic reactions, combustion reactions, there we go. So we're going to calculate the heat release and determine the enthalpy of fusion for water. So that's what we did. So you had these pre-lab questions, right? And that took you to this website right here. So hopefully you had the chance to go ahead and read through this. Hopefully it helps, explain a little bit more. I try to give you guys a few different ways to learn the material, and hopefully all of a sudden it clicks. So you had to go through there for your pre-lab question. So what is calorimetry? We talked about it, right? It's that change in energy of the system, that heat exchange is what it is. So what do we use a calorimeter, or what do we use calorimetry to do, right? To determine the heat exchange, right? The heat of fusion, that kind of thing. You can use it to figure out the specific heat also. So what is a calorimeter? Well, we just had a simple one, right? But so it's the device, right, that's going to measure that quantity, that heat transfer of your objects or of your reactions, depending on what you're doing. So I just copied and pasted here. What's the equation? So Q, heat, is equal to the mass times C, which is our specific heat, so that's a given, right? 4.186 for water, times our change in temperature. So you can see right there that we'll measure the quantity of energy gained or lost by the water. All right, so in your own words, explain how a coffee calorimeter works. So I just jotted down something real quick. So we have our system, we have our water and our ice. We're measuring how much heat gets lost from the water into the ice, and what's happening is you're breaking those bonds of the ice, right, and you're having that phase change. So we don't have a chemical reaction going on here. We have a physical reaction, right, a physical change going on. So we measure how much water we put in, right? We get that change of temperature. We can calculate how much heat it took or how much heat it lost, whatever, that heat exchange. And then from there, if it took, let's say, 1,000 joules, then we can figure out, okay, well, if 1,000 joules melted 100 grams, then we can calculate out that enthalpy of fusion, right? How much joules then per gram it took to melt. And we know for water that it should be 334. So that's what we're doing. This visual was on that website, so that heat exchange should be between the water and the system, right? It shouldn't be lost to the surrounding air. Ideally, that surrounding environment shouldn't be taking any heat or adding any heat, right? We don't want that extra energy involved. Just we use what we got right in there. So that's kind of what those arrows are for, like nothing, we don't want anything going in or out. And then down here you just had a little bit more explaining just kind of what we talked about. So what we have, so next step we have is we are getting all of our calculations, right? All of our data table here. So you went through, hopefully you went ahead and you went down here and you filled out your trial. So if you didn't watch this calculations help, you need to do that, because I'm not going to go through it all again because I already went through it in the video. So what you have is you have all of your data here, and I went ahead and I just, showed how I did it. And I do want to show you this too. So, I've done this lab how many times? I still go through, if you can see that and refresh, see my drawings? So something like this can get a little confusing, right? Like what needs to go where? What number am I using? So if you need, draw it out, just like I do here, right? It takes 2 seconds. I see that visual. And then I can think easier. Okay, if I this number minus this number is going to give me my water, right? My calorimeter minus my calorimeter plus water minus my calorimeter, right? And then I add in my ice. Okay, so how am I? What 2 things do I need to subtract, right? It's not that it's complicated, but when you have a huge list like this, it gets confusing. So just draw it out. Okay, so we went through and we got all of our data. So you should have done 3 trials. More than likely, your temperatures were pretty similar. They probably didn't vary a ton. But you can see down here that I calculated, my first trial. So I calculated the heat needed, right? So how much energy was transferred. So I had my water, right? I started with my 48 grams of water, and so 4,219.5 joules. It's not per gram, that's wrong. Joules. That's how much heat was transferred. How much heat came out of that water, right? That was the heat change. So then I can calculate out, okay, well, how many grams of ice did that amount of heat melt? Right? So that 4,200 joules of energy went into melting 14 grams of ice. So then I can calculate out that enthalpy of fusion, which is how much energy per gram it takes. When we're talking about, we're doing water here, right? We're changing that phase from a solid to a liquid. So my first trial was 301, you can see, my second 322, and my third 359. So then I can calculate my percent air, right? The absolute value. So what I got, minus theoretical divided by theoretical times 100, absolute value, no negatives, right? So you can see my 3 different percent airs. And then lastly, I calculated the average percent air. So I'm not going to calculate the average percent air off of taking my 3 averages, because since we're doing absolute value, that 9.9 was low, that 7.5 was high. Well, since they're all in the positive, that's not really going to give me a good gist of how well I actually did, right? So you're taking your average percent air off of your enthalpies. So up here I averaged my 3 enthalpies, add them all together, divide by 3, right? And then I did the calculation. So my average air was 1.9, which is pretty good, right? 1 high, 1 low, 1 pretty solid in the middle. All right, so your post-lab questions, we just did that, right? I figured out my average, went ahead and calculated it. So the last thing that you needed to do was talk about sources of air. So we haven't really talked too much about it so far. So what I did was I gave you a nice website. This was a really good website. You can go right here. It's cutting it off a little, but you need to make sure you read through those because you'll have questions about this on your test. So talking about air, right? Don't give me the thermometer could have been off. Oh, I could have not zeroed out. Those are basic, right? Those are just typical things. We want to dig deep and we want to look at what in this specific lab could have happened and how would it have altered my results, right? That's ideally what you want when you think about your percent error. How would that have affected the value you got for your heat of fusion? So make sure you check out those if you didn't. I just have a list here of a bunch of different ones that I've gathered over the years. So again here, human error, yeah, especially miscalculations, like no, those aren't good, right? So if you did those, go back through and think specifically what could have happened. Not a temperature, not having a balance incorrect, not having a thermometer incorrect, not, what else? I don't know what else you could have put. But those 2 things don't do. Okay, so stirring, right? That's not really human error. Wouldn't look at that as like a human error because stirring is a main part of that, right? You got to stir that. So talk about it. Stirring. What's that affecting, right? If you don't stir, what's it going to affect? It's going to affect the temperature, right? And how is that going to affect then your results? So that's what I want you to do. So this says, it might not have melted to the full capacity, which is true, right? I mean, when you put an ice cube in a hot drink, you stir it for a reason, right? To cool off the whole thing. You just plop it in there and let it sit, very different. So explain that, and then explain how that temperature difference, right? Let's say instead of 21, it was only 15 difference. How is that going to affect your enthalpy then? Insulation, you could talk about your system as a whole. If it's not insulated well, if you're losing heat to the to the surroundings, that kind of thing. Let's see. I know one was opening the lid, losing heat. And then there was talking about ice or pouring out the water. Like if you accidentally poured out some ice when you poured out the water, how would that have affected your results? What if you didn't pour all the water out? How would that have affected your results? So those are specific to this lab. So that's what you want to focus on for your 3 possible sources of air. So I think that's it. So you have that first keyword. Here's your second keyword. So when you fill out your quiz, make sure that you're putting both in there. And any questions, let me know, and we'll talk with you soon. Thanks.